Okay, can you see my screen?
Yeah, that looks good.
Is the mic good enough? Tell me if it's not, and I'll just get going.
Sounds good.
Okay. Okay, so apologies, I've missed my introduction. I'm Andy Shepherd. I'm going to give a presentation. I'll try to speed through some of the things that I think will be of less interest to you guys on other aspects of the mission. This is a presentation that I put together about some of the satellite observations that CryoSat has made because they're particularly relevant for sea level rise, which I guess is the theme of your seminar series. And it's built mainly from work that my group have done over the past 10 to 20 years on polar altimetry in general. So we've progressively used satellite altimeters to look at different parts of the cryosphere. And started out, my first measurements were on Antarctica, but we've moved around to look at progressively harder and harder elements. And so they've eventually added up to look at all parts of the cryosphere, and in particular using CryoSat as the backbone, but we learned from that mission to be able to use other satellites as well. There's a lot of work in this presentation that isn't just mine alone, and it stems from people who've either been through our group over the past 10 to 20 years or are still with us today. And in particular, my PhD students. A lot of the students that have come through my group are still active in polar science, and they're working around the planet in different locations. And most of the work that I'll show today is derived in one way or another from their project. So I need to give special credit to them because it's without their work, I wouldn't be able to show most of these things that I'm going to show today. So I'll talk about ice and climate. I'll talk about CryoSat 2 for those of you that don't know enough about it already. I'll talk about polar science, and then Earth's ice imbalance, which is a synthesis paper that we published earlier this year about different parts of the cryosphere, some impacts of the ice loss, and actually what we can do about it. I've increasingly become aware that people, this isn't a good news story. So people end up leaving my seminars or lectures these days in a less good mood than they arrived. And it's just because I'm too close to the subject area that I've often thought that this is wonderful. We can see these things from space. But actually, it's not a great story at all for most people who are just a general member of the audience. They just see bad news all the way through it. So I've tried to give more attention to things that we can do about it these days towards the end, and the things that offer some hope for the future. So there are lots of changes happening on the planet, and the wonderful thing about the cryosphere is it kind of responds first. You all know that. It's a barometer for change, but that actually means, the only reason I'm telling you this is that actually means that it will be the one to recover first as well. And this is the way that you can pass on a message to people that the changes that we've seen in the cryosphere, which have been quite dramatic over the past 10 to 20 years, certainly for the past decade, could flip backwards again. And so we should be looking to the record of cryosphere change that we've got from satellite measurements to try and spot these early signs of recovery. And that's what I'll be telling my team to do over the next 10, 20 years, rather than continue to report huge losses of ice and the total amounts of ice that have been lost, although that will be a large part of what I'll talk about today. So there are two parts of the cryosphere. There's the ice that's on land. This is a wonderful game that Anne LeBrock and others produced for Key Stage 2 and 3 kids to teach them how a glacier system responds to changes in forcing, so changes in snowfall or changes in ocean melting, and they can cause penguins to survive and things like this. But this teaches you the basics about ice sheets, the grounded ice sheets, and how they respond to climate change. And we know what happens, except we've learned what happens, mostly because of the satellites that we've had in space, and then the numerical models which have been improved as a consequence of the satellite observations. And then there's the ice that floats on the sea surface, and that's a different part of the cryosphere. It's the frozen ocean, mainly, and there's still some icebergs that drift around too. But in the case of the sea ice in the southern hemisphere, it's the frozen ocean. It's a very different part of the system, plays a different role, but it's also exhibiting change, and we can monitor it with the same satellites that we use to look at land ice. And there are parts of the planet that have changed dramatically since during the satellite era. And I say satellite era, really referring to the 1990s onward, when we had dedicated environmental satellite missions. There are some satellites before then, but these are the periods where we have consistent observations. This is Prince Gustav Channel at the Antarctic Peninsula. And you can sail through Prince Gustav Channel now because the ice shelf that was previously occupying it, Prince Gustav Ice Shelf, collapsed in 1985, around that time, between 1985 and 1990. It disintegrated and it's no longer there. So you can sail between the mainland Antarctic Peninsula and Ross Island here on the right through this channel. And you can do some geology and you can learn about past environments thanks to the collapse of the ice shelf and wonder about what the collapse of the ice shelf actually means. And you'll have seen lots and lots of people talk about collapse of ice shelves. This is some work that I did in the early 2000s on Larsen Ice Shelf, looking at changes in the ice shelf structure prior to its collapse. And the easy thing to do is look with satellite images. So this is 1986. That's when Prince Gustav Channel started to break away. And you can progressively march through a time sequence of satellite images to see the collapse of the various ice shelf sections. And then we can watch afterwards what those collapses meant. But before they collapsed is the real thing that we're interested in, to try and understand what conditions came about to allow them to collapse. But after they've gone, you can do wonderful things. You can sail ships into the embayments and you can examine the sea floor to see whether there are any traces that you can use to interpret the environment, the previous environment and the present environment. And this is a wonderful photograph of the seabed beneath the Larsen Ice Shelf after it had collapsed and drifted away, collected by Carol Pudsey. And she sent this piston core down onto the seabed and a wonderful camera as well. And for the geologists amongst you, you'll already spot that there's something, a telltale sign here. There's an erratic boulder on the seabed. That erratic boulder can only have been dropped from an iceberg, which means it was dropped after the ice shelf had collapsed because the iceberg wouldn't have been drifting in the ocean. And so looking at the provenance of the material on the seabed, you can learn a lot about the environment. So if you take the piston core out of the seabed and analyze the sediments, you can find these foraminifera, and you can identify through the sediment layers the foraminifera that like to live in light environments and those that like to live in dark environments. And then you can date them using geological dating techniques. And you can learn, for instance, as Carol did, and Gene Domack in the States as well, that this ice shelf had been there for 10,000 years. So this tells us the big picture that the ice shelf collapses are unprecedented during this glacial period. And so we need to wake up and listen to the changes that are happening. And then when the ice shelves have gone, you can just fly around. This is Crane Glacier, the Antarctic Peninsula. And you can see very clearly a trim line here. The glacier has retreated since it collapsed and left this trim line exposed, which was where it formerly was. It was 20 or 30 meters thicker before the ice shelf collapsed. You can use satellite measurements to look at the speed of the ice. This is Drygalski Glacier, and that glacier is now flowing 8 times faster now that the ice shelf has collapsed in front of it and pouring ice into the ocean. So this is a really important story for climate science because it links changes the environmental conditions today to abrupt shifts in the climate system. And we just had a seminar from Petra about tipping points. Well, this is a tipping point. This has actually happened in our lifetimes. We're not going to be able to reverse these changes without a huge reforcing of this system to allow it to grow a 500-kilometer ice shelf back in front of the glacier, which will take 500 years. It's not going to happen anytime soon. And not only is it irreversible, essentially in our lifetimes, it's caused sea level rise because the glaciers are now flowing more quickly. And we've learned a lot about the stability of these systems thanks to the satellite measurements, not just of the post-collapse conditions, but also the pre-collapse conditions as well. Those ice shelves are quite small at the Antarctic Peninsula. They're not the big deal, the big ticket items. You know, it's Pine Island and Thwaites in Antarctica and Jakobshavn and Northeast Greenland Ice Stream in Greenland. The ice sheets themselves have huge sea level potential. And the question really isn't how much sea level is going to come from the ice sheets, it's how quickly it will arrive from the ice sheets. And so that's the question that we try to refine with the numerical models. And it turns out that the satellite observations are really helpful there as well, because we see in the satellites changes in the satellite observations, changes in the climate system that are not incorporated in the numerical models. And here's 3 examples that I used to show a long time ago, and they weren't in the numerical models in the early days. So there's basal lubrication of the ice. We learned about that really because of the changes that were happening on the Greenland ice sheet, the seasonal variations in the flow that were being driven by the meltwater at the surface. That process is now incorporated in climate models. Iceberg carving and ice shelf carving, well, that wasn't thought to be a big deal in the 1990s. I can tell you in the 2000s, there was still a raging debate in the glaciological community as to whether ice shelves mattered, but they do. And now the numerical models are improved to properly represent those processes. And ocean melting, well, that's the big driver of most of the changes that we see around the planet today in the cryosphere. And the ability to simulate those changes, it depends entirely on how well your cavity circulation model is and how well you represent the discontinuity interaction of the grounding line on the ice shelf. So these processes all need refinement and have needed refinement and have been improved, but that's largely thanks to the satellite measurements, which have told people that the historical models were lacking. So let's go back to the early 1990s. Second IPCC report, 1995, not so far away in the past. Look through that, flick through it, and you'll see that the cryosphere was expected to grow in a warming climate, even then, 1995. So this is a consequence of increased temperatures, increased precipitation. That should lead to growth of an ice sheet, all things being equal. And that's because the ice sheets, it's not all because the dynamic, mainly because the dynamical imbalance wasn't properly understood. And things have changed obviously since then. But the reason I'm telling you this is because this is when CryoSat was pitched against the backdrop of real uncertainty as whether the cryosphere really mattered. And this is the way that satellites have to be pitched, decades ahead of when they fly. So you have to be prescient about the signals that you will need to monitor in the future, because your satellite won't get launched for 20 years at least. And you can talk to the ISAT team about that as well, and they'll tell you exactly the same. So you don't often know the classes of measurements that you need before the capability is available. And so it's thanks to the people that proposed CryoSat in the 1990s that we have the measurements in the 2010s. And that's really, really important, because if I get to the end of this seminar, we're going to have a gap in polar observations because we didn't do a good enough job. I didn't do a good enough job of persuading the space agencies that we need continuous measurements in the class of polar altimetry. And this is why we need CryoSat. This is really the main motivation for CryoSat at the time, was the Arctic sea ice cap. So this is how the polar altimeters, well, the near polar orbit altimeters, ERS-1, 2, and ENVISAT, saw the Arctic in the pre-CryoSat and IceSat days, missing a huge section of the Arctic sea ice cap at the North Pole. Because it's a mobile chunk of ice, any survey not including that region is partial. We don't really know what's happening in that area. So you don't know that trends in sea ice are not related to compaction and drifting of the ice into a smaller area in the middle of the Arctic Ocean. So we have a satellite, really not a very sophisticated thing. It flies over the polar regions, which is the sort of genius moment that you would have expected somebody to have earlier on, but they didn't. Just stick a satellite covering the polar regions, and then you'll be able to tell people about the total amount of sea ice because you're observing more or less all of it. And the same is true for Antarctic ice as well. We're not just interested in the sea ice, of course. We're interested in these events that are happening at the other end of the planet too. And so collapse of the ice shelves has been a real motivator for looking at changes in the cryosphere as well, because that was a signal that we knew about sooner than we heard about Pine Island and Thwaites, for example. Those signals only really emerged in the early 2000s. The first paper was really Eric Reno's and Duncan Wingham's in 1998, which told us about changes in the Amazon Sea. Prior to that, all of the logistical effort, particularly from the US with the huge polar program, was over at the Cyprus coast in entirely the wrong part of the continent, just because theoretically this was the most likely place to exhibit collapse, because we had marine sediments beneath the glaciers. Well, it turns out that the Amazon Sea was the place that we should have been looking all along. And so the genius things that CryoSat had was it was flying over the polar regions, but it also had a high spatial resolution altimeter as well. And that allows us to see the leads between the sea ice flows, which is important for monitoring sea ice thickness, but it allows us to see the outlet glaciers in the polar regions as well, which is really important because that's where they're most dynamically active. And so we have to see these parts, not just the interior, which is more or less stable. And so that's all that CryoSat has really on it. And it's the same for IceSat. It just uses the laser to do the same thing, IceSat 2 now. So CryoSat was first launched on a rocket that didn't let go of it. So it took it back into the Arctic Ocean, and CryoSat 1, in fact, is still surveying the Arctic Ocean. You can see this in the publications track record of the mission. So there was a small peak going up to the launch of the original CryoSat 1 in 2007, which failed. And then CryoSat 2 was launched in 2010. And the rest is history. We had a decade of measurements now from the mission. So I want to talk about the polar science that we've managed to achieve with CryoSat really quickly across lots and lots of different domains. But I want to come back to, in particular, the ice mass balance budget, which is presumably what you guys will be more interested in. But just to give you a flavor of the data sets that we're able to produce from the altimetry. Well, this is the state of the art before CryoSat. It's a blended elevation model produced by John Bamber and Bob Binchadler of the Antarctic ice sheet. It's a mixture of radar altimetry from the early 1990s and a cartographic elevation model, but it's still beautiful. If you're an Antarctic scientist like me, it's a beautiful map of the continent. In the early 2000s, this was the state of the art. Maps of elevation change for Antarctica, partial because the satellites ended up being switched on and off in certain times, and very coarse resolution, and with terrible color scales because none of those things had been improved until the modern day at least. But even in this data, published in 1998, you can start to see a signal emerging in the Amazon Sea. So there's significant thinning, about 10 centimeters per year over a 3 or 4 year time period then. We replaced it with an updated map produced from Envisat as well. So about 15 years of data now, higher spatial resolution, different color scale. You might not like it, but it's still a sort of rainbow, but this was IDL back in those days. Didn't have MATLAB in these days, or at least I didn't. And then now the complete picture of 25 years of altimetry shows very, very clearly the signals of dynamical imbalance that I'm sure that everybody on the call is familiar with. 1997, the ice sheet was really just starting to witness these dynamical instabilities. By 2017, 50% of the Amazon Sea basin has now become dynamically activated. So that's in a generation, in 25 years, half of the drainage basins are now unstable. And that's a significant shift, even during the satellite period from when we've had observations. And you can track the inland spreading of that signal through the altimeter record really nicely. So the beautiful thing about altimetry, it might not be the best tool for measuring mass balance. Your friends who work with GRACE will tell you it's the best tool for measuring mass balance, but it's the best tool for glaciology. You can see all the glaciology that's happening in the polar ice sheets or in the sea ice, thanks to the spatial resolution and the temporal resolution that you get from the altimetry. And so that's where it comes into its real strength, because it gives us this continuous record. In Greenland, we see a similar signal, but Greenland has a more complicated driving mechanism because it suffers a lot from melting in summer as well, and there's a strong seasonal cycle in accumulation and melting to take into account, which we don't really have in Antarctica. There's not really any melting. So this is the pattern of elevation change in Greenland, which you'll be familiar with, coastal thinning, inland stability. But this is the pattern of elevation change driven by surface processes from a regional climate model. In this case, it's the IMO-RACMO regional climate model. And they look similar. When you take one from the other, you see the dynamics. And again, this is thanks to the altimetry coupled with a regional climate model. The dynamical instabilities are really obvious now. You can see those glaciers. You could see them mixed in with the surface mass balance signal on the left, but on their own, it's a really clear signal. There are some other features in there which the real glaciologists will be interested in. The blue lines are, Mike McFerrin and co talked about those last year in their Nature paper. They're ice lenses, ice slabs, which are forming in the ice sheet because it's changing its near surface firn stratigraphy structure, for instance. And so there's lots of glaciology in here over and above the dynamics, but you can see the dynamical instabilities. And when you put them next to one another, you see similar sorts of scale thinning in the ice sheets, bring in the ocean forcing, and you can see what's driving most of that imbalance. Its changes in ocean temperature are driving instability in the marine terminating sectors of both ice sheets, in particular in West Antarctica and at the Antarctic Peninsula, but also around West Central Greenland. Lots of the changes are driven by ocean melting. We're also interested in grounding lines because they tell us about instability in particular, but tell us about whether that instability is rapid enough to cause a collapse of the marine ice sheet, for instance. So the grounding line is a hard place to access. In West Antarctica, it's a kilometre below sea level. And so we look at the surface flexure instead. So the bit of the glacier system that's floating in the ocean moves up and down with the tides. And if we can map this flexure over time with altimetry, we can chart the location of the grounding line. But also, if we know the location of the grounding line, we can translate grounding line thinning to grounding line migration. And so this tells us, gives an early warning system for Antarctica, tells us where the rate of migration of the grounding line is faster or slower or similar to the rates of retreat over the Holocene period, which we get from the geological record. And it's no surprise that all along the Amundsen Sea, Bellingshausen Sea, the grounding line retreats are 100 times faster than they have been during the Holocene period. And so these are the places we need to be concerned about. Ice shelves are a more complicated story because they're floating. We only see a proportion of their thickness and therefore a proportion of their thickness change with an altimeter. So it's 10 times harder to track changes in ice shelf thickness than it is to track changes in grounded ice thickness. But we can still do it. And so this is an early map we produced in 2009 of the thickness change on average for ice shelves. Sushil Adusamili has done a very much better job using the long record of altimetry now, and he's shown that the elevation changes that have fine spatial structure, the thickness changes in the ice shelves, but they're also correlated with the warm ocean around Antarctica too. And so this is the coupling that had to be introduced into the ice sheet models in order to properly represent the forcing that we were seeing from the ocean. If your ice shelf is not properly represented, it won't respond to ocean warming in the same way as if it were. And if the ice shelf is not coupled to the grounded ice and to the ocean, then you can't expect any feedback mechanisms to be properly realized. So this has driven changes in the representation of the land ice junction, in particular within ice dynamical models. When it comes to sea ice, we can do quite a good job in the Northern Hemisphere. We can track changes for 7 months of each year in the thickness of sea ice, and we can do that from probably the early 2000s, really. This time series shows the CryoSat record, but we can then extend backwards with ISAT-1 or ENVISAT. And indeed, there are plans to go back to ERAS-1 and ERAS-2 as well. It's coarser resolution and it's less reliable, but it's still a record of the change. And we can even start to look at, thanks to having two satellites, classes of satellites in orbit at any one time. Today it's IceSat-2 and CryoSat-2, but in the past it was Altica and CryoSat. We can look at differences in the scattering horizons, which tell us about the thickness of snow on top of the sea ice, which is one of the real challenges that we have in the Arctic in particular, but also in Antarctica. We still can't measure Antarctic sea ice from space. So if you want a job in the future, take a look at Antarctic sea ice, because that's the last frontier really for Earth observation. It's a real challenge because it snows a lot down there. We can see mountain glaciers. CryoSat has an interferometric mode, which provides, as its baseline product, a single measurement of elevation on the ground track as the satellite flies over. And this is what that elevation might look like in Greenland, northwest Greenland. It's Petermann Glacier. But if we apply full interferometric processing to the data, which we can do, then you can fill in the gaps and you can get a spatial map, the continuous spatial map of the elevation now, which looks like a swath LiDAR altimeter, in fact, with about a 500-meter footprint, maybe 250 meters if you're lucky. You can stack that over time. This is now Vatnajökull in Iceland, topical. I hope you've all seen the absolutely fantastic drone footage from Iceland yesterday. If you haven't, take a look at Twitter. But Vatnajökull, this is the elevation change from the baseline CryoSat data. If we fill it in with the swath processing, we can see a very, very clear picture of marginal thinning and growth in the interior. This is how we expect all ice sheets to respond to climate warming, all ice caps, should I say. They're land terminating. They'll grow in their interior because it will snow more, and they'll melt at their margins because it will melt more, and they'll become progressively a different shape. They'll become steeper sided over time. And that's what's happening. Iceland will probably lose all of its glaciers in the next 50 years as a consequence of climate warming. And we can look at icebergs as well. So follow John Amos on Twitter and you'll learn about icebergs. He'll tell you all about icebergs all of the time. But this is one of the most famous icebergs at the moment. It's A68. It broke away from, it's not the most famous actually, it's been bumped off because the Brunt iceberg is more important because it's next to Halley Base. But A68 broke away a few years ago, very large iceberg, represents an actual ice loss from the continent because it was previously attached, even though it's floating. A small sea level contribution, 2.7%, it's already afloat. And it's been drifting around in the Southern Ocean since it calved away. And there was a concern that it would drift into the South Georgia Island and cause devastation to the communities that live around there, not the people, the marine communities that live there. They don't want lots of fresh cold water dumped on their island. And so we can track that iceberg. We can track changes in iceberg thickness over time. It's a much harder thing to do because they spin around, but we can do it. This is some work done by one of the students who works in my group, Anne Brackman-Folgman. And she's charted, in this case, it's the Thwaites Glacier iceberg over time, but she's moved on to look at the A68 iceberg. And she's tracked the thickness and the thickness change of this iceberg over time. And that told us that the iceberg was too thick to ground around South Georgia, which is important because it didn't become this ecological disaster that people were worrying that it would, because it was just too thick, it never got there. And we can also look at subglacial lakes. You might have heard about subglacial lakes. They live beneath Antarctica mainly. There are one or two beneath Greenland. And we don't see the subglacial lakes, we see the surface expression. And we've learned in the past 20 or so years, 15 to 20 years, that water moves around beneath at the base of the ice sheet. It doesn't stay put. It doesn't sit in these lakes forever and their pristine environments. It moves around between one lake and another, forced by the pressure head that's existing beneath the ice sheet in the hydraulic drainage network. And sometimes that will cause a lake to drain upstream, and sometimes it will cause a lake to fill downstream. And we see the surface expression of those features, and we infer that this must be due to water moving around at the base of the ice sheet. There are lots of these lakes now mapped around Antarctica, and people are interested in them because they might be repositories for extreme life, for instance. And so people want to learn more about the ice sheets, not just simply the amount of ice that's stored in them. And so we can use the altimetry measurements to look at very, very obscure glaciological processes like this. And we could also look at the oceans as well. I'm not an oceanographer, but oceanographers love CryoSat because of its drifting orbit. Its drifting orbit means you get a continuous pattern of elevation across the surface of the global oceans, which you can invert to look at marine gravity anomalies, which can then in turn be inverted to look at the depth of the ocean column. And so we can map the bathymetry of the sea floor in far finer detail than we could from a conventional altimeter, because it has this fixed orbit pattern. So we get fine spatial detail. And Dave Samwell and others has been able to also make use of the measurements to track sea level rise. So CryoSat itself is monitoring sea level, and it provides higher fidelity observations just because of the spatial sampling, particularly in the polar regions as well, where we can remove the signal due to the sea ice cover. And so we can track changes in sea level around the planet and then see whether they balance against the ice losses that we're seeing from the grounded ice sheets. And in the main, they do as well. But we can also track dynamic ocean currents as well. This is some work from Tom Armitage and others. So if you put it all together, we've got a complete picture of the cryosphere, except for Antarctic sea ice, thanks to high resolution satellite altimetry. You could build a similar presentation from ICESat-2 measurements if the satellite had been in orbit for 10 years. It hasn't, but hopefully in a few years' time, it will stay up there and it'll be able to monitor similar things. The ideal situation is that we have a continuous monitoring capability for polar altimetry going forwards. So I want to talk about Earth's ice imbalance, if I've got a few minutes, if I haven't wasted all of my time. Earth is covered in different types of ice. And so this is a map of the cryosphere, a static map here, and it shows those different types of ice. We've got the Greenland and Antarctic ice sheets on land. We have ice shelves mainly fringing Antarctica, and they're the lateral extension of the floating ice. And then we have the sea ice in the Southern Ocean and the Arctic Ocean, which waxes and wanes with the seasons each year. More or less, there's about the same amount of sea ice on planet Earth at any time. It's just some of it is in the Southern Hemisphere and some of it's in the North. And then we have mountain glaciers as well. And all of these bits of ice form Earth's cryosphere. It's the ice part of it. There's other parts of the cryosphere, permafrost and snow, but they're not ice. And so this is Earth's ice imbalance, the amount of ice that's stored in ice form on our planet at any one time. And it's a paper that we put together during lockdown, actually last year. We're really pleased to see it out. And so it's looking at the various components. And this is New York City for scale. So it's Manhattan, actually, mainly. And this is the simple way we found to represent the total amount of ice, because people don't really relate to what 1 billion tons of ice might look like. It's a cube of ice, a certain size. So if you look at mountain glaciers, this is the time variation in the amount of ice stored in mountain glaciers, thanks to CryoSat and some other observations as well. They've lost 266 gigatons, billion tons of ice per year over the past 25 years or so. The Greenland ice sheet has lost 166 billion tons of ice. Antarctica has lost 111 billion tons of ice. And the floating ice shelves around Antarctica have lost 284 billion tons of ice, either through melting at their base or breakup. We've seen some examples of that earlier on. Arctic sea ice has lost 329 billion tons of ice per year. And even during this period, the Antarctic sea ice pack shrank by 40 billion tons of ice per year. So that's 1,000 billion or 1 trillion tons of ice per year lost from the cryosphere. And that's a 10-kilometer high cube of ice. And that's a huge amount of ice, of course. And it would be impossible to replenish that in any short time scale. And where is it on a map of the ice? So most of it came from floating ice shelves, actually, either breaking up or melting around Antarctica. They're a really important part of the climate system because they provide cold, fresh water, which is the southern dipole of the thermohaline circulation. Without it, we wouldn't have vigorous overturning and warm conditions at sometimes in northwestern Europe and northeastern US. And so we depend upon these ice shelves. We don't want them to go. They keep us in a habitable environment. They're losing the most ice of all individual elements in the climate system. Arctic sea ice is the next biggest loser. We know about the shrinking of the Arctic sea ice, but what's more important, or just as important, is the change in the thickness, which tells us the total amount. Because it's mobile, a change in area alone doesn't tell us whether there's a change in the amount. We need to measure the volume, but it is reducing by 329 billion tons per year. Mountain glaciers still contribute a large amount, even though they have the smallest sea level potential. They're still contributing a huge amount to sea level rise, 266 gigatons per year. And then we have the Greenland ice sheet, relatively small, but actually, along with Antarctica, which is also relatively small, these are the major concerns for future sea level, which I'm sure you know about, because their rate of ice losses increased by a factor 5 or 6 over the satellite period and doesn't show any sign of abating. And then even Antarctic sea ice is showing a retreat. So what might the impacts of this be? Well, if we plot the rate of ice loss from the grounded ice sheets, in particular, Antarctic and Greenland, over time, we can see that acceleration. It's now 5 times faster than it was in the 1990s. The total contribution is quite small, 18 millimeters, but then put it next to the IPCC projections, and you can see very clearly that we're actually tracking the high-end scenario for ice loss. This is not RCP 8.5. This is the high-end scenario for ice sheet response to any of the emission scenarios. And so we're tracking that upper range, which means the models are under predicting the rate of dynamical imbalance for Antarctica and Greenland. And that's a really important consideration, because by the end of the century, it's an extra 17 centimeters of sea level rise. And if things continue, we should be planning for that. And does that matter? Well, this is close to where you all live, I think. This is New York City. This is Lower Manhattan during Hurricane Sandy. This is not a trivial event at all. This was a really serious event for the US. I think 46 people lost their lives in this event, and 50 square kilometers were flooded. And this is a once in the millennium event, right? This is a spike in sea level that was a confluence of persistent storm sitting over the location and causing pluvial and coastal flooding all at the same time. And you can see that in the tide gauge at Hudson, at Battery. There's a huge spike in the water level, which is not normal. and isn't likely to be reproduced anytime soon. And you couldn't really easily accurately model that spike. But this is what happens if you change sea level by that 80 centimeters. Then these events become more common. You must have seen this before. We have similar plots for other coastal places in the country. And we need to move away from the displacement, the convenient displacement that it's about inundation. It's not, it's about episodic flooding. And I'm sure that you all know this anyway. And it happens here where I live in the UK as well. This is the coastline of the county. I live in Yorkshire in the UK. And this is our coastline. It's eroding. People are losing their homes to either coastal erosion or to flooding. These two things devastate coastlines. And we have to plan for managed retreat because it's too expensive to protect these coastlines. But in other parts of the world, people are already planning to protect their coastlines. We heard in our seminar about the Netherlands because Petra Langebroek is Dutch, and they build dikes around all of their cities to protect them. But there's only so many dikes you can build before you have too much water to withstand. And so this is also a controversial piece of data. This is Kulpenstrauss. I'm sure you've seen this too. This is the predicted population that will be displaced or will be affected by annual coastal flooding in the world as a function of sea level rise. And there's a lot of people. They already estimate that 250 million people around the planet are exposed to annual flooding, and that's a contentious number. But their prediction is that by the end of the century, an extra 100 million, depending on the scenario that's tracked, will be brought into a situation of annual coastal flooding. So that's about 3 million people per centimetre of sea level rise. So if you want to think about how much sea level rise has an impact, 3 million people per centimetre is a useful metric. And so that extra 17 centimetres is going to mean an extra 50 million people are brought into a situation of annual coastal flooding. And that's irrespective of the coastal erosion that might happen. And so this is the plan. You must have seen this, Bill de Blasio. He's got a plan for downtown New York, protecting the central business district, not where people really live. And so this is $10 billion to pay for this. And you can do that in New York because there's a bit of ocean that you can reclaim. You can't do it in San Francisco. They already reclaimed their coastline. So it's not going to work there. They'll have to think of something else, unfortunately. And that will be expensive. There's a $600 million wall being built around SFO, for instance. And these things can be paid for if you're wealthy, but they can't be paid for if you're not wealthy. So the question is then, can we help? Can we as scientists do anything about it? Well, you can definitely campaign, and you can encourage people to eat less meat and drive their cars less and things like this. But there's science that we can do as well. And so this is a model realization of ice sheet collapse in the Amazon Sea. It's done with the Bicycles ice sheet model, which my center runs. And it's an evolution over the next 300 years of Pine Island and Thwaites, and it shows the collapse into the future that might occur under one realization. And the question is this realistic or not? So what we can do with the satellite measurements is we can look back over time at the models and see whether they've improved. So this is AR1. At that stage, it was assumed that the Antarctic ice sheet would take sea level away and offset the ice losses from Greenland. So Greenland would make a contribution to sea level rise, but Antarctica would offset most of that contribution, and there would be a small contribution to sea level rise. In AR2, it was even less. It was net zero between the two ice sheets. They were balancing one another. AR3, it was worse still, net positive. Antarctica was going to save us from sea level rise. It was only in AR4 that ice dynamics started to be brought into those models. And this turned the tide, forgive the pun, from dominated by Antarctic growth to retreat associated with both ice loss from Antarctica, but also increased losses from Greenland. In AR5, both ice sheets contribute to sea level rise in the future. And in fact, those measurements line up quite nicely, certainly within errors, to the satellite observations. And that's a really, really good illustration of how during the satellite era, we've also lived through the model era, where Earth system models have started to be generally representative of the changes that we see on Earth. And that's largely thanks to the satellite measurements that we've had in tandem with those model developments. And so if we move into this new situation where we hope that our governments will encourage people to reduce emissions, then we can start to track progress against emission scenarios. And this is a good example. We can track the ice losses from Antarctica and Greenland. I've already showed it you today, and we're tracking the worst case scenario. I'm not going to show it now because it's still embargoed, but we've produced an update for the IPCC of the IMBY assessment. And things are looking a little bit better. We're no longer tracking the high-end scenario. Maybe one day we'll drop back down to the mid-range scenario, or even down to the low-end scenario. And we'll see it first. We'll see the responses first in measurements of the polar regions. We can build satellites, and this is a plea to everybody. If you are asked if we need new satellites, please say yes. And if you're asked if you want to work building new satellites, please also say yes, because we need people to make the satellites for the future. There's going to be a gap. I hope I've done a good job of showing how powerful satellite altimetry is, particularly for looking at the polar regions. Well, there's going to be a gap. We've had a succession of satellite altimeters because of people who, some of whom are dead now, were building them and designing them in the 1970s. And up until today, when we have CryoSat 2 and IceSat 2. But there's going to be a gap. There's no mission commissioned yet. The European Union is considering a mission called Crystal, which, if it gets approved, will probably fly in 2030. CryoSat's 11 years old. It's got a fuel leak. It's time limited now by its fuel leak and its battery degradation. IceSat 2 is time limited because it's lasers, and lasers they sound cool in space, but they don't last forever. And so we'll have an altimetry gap in the polar regions of about 5 years, even if the European Union commit to paying for the follow-on mission Crystal, which won't really launch until the 2030s. So we'll have to use something else to learn about the cryosphere and to monitor the cryosphere in the intervening time period. So CryoSat will be gone. IceSat 2 will almost certainly be gone. The next mission will come in 2030 or so. We could do something with these missions. We could prolong the lifetimes, perhaps, of the missions that are still up in space right now, or we could bring forward, accelerate Crystal, for instance, to reduce that gap. We could steal another satellite, like a Moonraker type thing, or Austin Powers. There are tons of satellite altimeters just staring at the global oceans right now, and the European Union has 4, at least 2 in warehouses. We could take one of those, for instance, and people could choose to do that if they wanted to. We could fly some CubeSats. Some people think they're confetti, other people think they're wonderful and the future of new space. We could fly a cheap CubeSat and to bridge the gap, or we could reinstate for something like the US Iceberg program to continue the observations in the event that both CryoSat and IceSat die. So I'm sorry I had to skip really quickly through that, but it's my fault for being slow. So I just want to end on some headlines. Sorry, my fault for missing the start time. So I want to finish on some headlines. So CryoSat is now 10 years in space. Its manufacturer's guarantee is 3.5 years. So it's doing well, right? It's better than your vacuum cleaner for sure. And it's still going to live for some years, I'm sure of it. I'm the principal scientist, where we have mitigation plans to offset the effects of the fuel leak and to offset the degradation in the battery. And we want to keep it in space forever, but we're realists as well. No altimeter has lived 15 years or more, and so we don't expect it to last forever. It's exceeded its mission objectives, and it's now monitoring all components of the cryosphere. It has capability far beyond the original mission objectives, and the data are integral to assessments of global ice imbalance. The bad news for global ice imbalance is really bad news. 28 trillion tons of ice has been lost. 1 trillion tons of ice per year. All parts of the cryosphere are losing ice, no matter where you look, every corner of our planet. And we need to do something about that. It's going to affect coastlines everywhere, and irrespective of whether you live at a coastline, you almost certainly make use of it, even if you don't know it. And so people will have to do something about their coastal areas in the future to address the increased flooding that's likely to occur. And our challenge as scientists is to improve those models, to make them more reliable. We don't want to be tracking the high-end scenario. We want the mid-range scenario to be representing the changes that are actually happening on Earth today. We need to invent a new high-end scenario effectively. And we need to build new technology to plug this gap in observations that will be coming. So I want to end on that. Thank you.
Thanks so much, Andy. That was a really nice, rather inspiring at times talk. I see Johnny's clapping. I should have some canned at the end. So there are a couple of questions in the chat which maybe we should get onto first, and then I'll open things up. So I noticed Vivian was somewhat furiously posting a number of questions throughout the talk. Is there any chance you'd like to unmute Vivian and ask a couple of these, or I could?
Yes, sure. Yeah, I think we mentioned about bridging the gap. I had a question about that, but I mean, I think that was discussed. But you said that CryoSat was unable to monitor Antarctic sea ice, and why would that be?
So all of our altimeters struggle with Antarctic sea ice, and it's not really a technical problem. It's because it snows a lot in Antarctica, and what happens is the snow piles up and it pushes the ice freeboard to sea level, and then our measurement from radar altimetry is of the freeboard, and if it's at sea level, then we don't have a signal anymore. And so as soon as the snow load piles up enough, then we lose a capability to monitor its thickness from space. IceSat sees the snow freeboard, it sees the surface of the snow layer, but they also have the problem that they don't know how thick the snow is either. So the perfect scenario is the one that we have right now. We have both satellites in space at the same time, dual frequency. CryoSat sees through the snow to the ice freeboard, and IceSat sees the top of the snow, and we have two unknowns and two measurements. And so with those two satellites, we should be able to solve this problem.
Well, you mentioned the thickness of the ice. What about changes in aerial extent?
Oh, well, the changes in the aerial extent are really super important, but we could measure them with an altimeter, but you don't need to because we have the passive microwave. And so the passive microwave gives us a good measure of the concentration and the extent. And the altimetry gives us the thickness, the third dimension. And so the two things together give us the volume.
Mm-hmm. All right, and the other question was simply, I was curious about the reference. You mentioned something about population below mean high tide.
Yes. Culp and Strauss, Nature Communications, highly contentious paper. They work for Climate Central. They're great guys. But it was based upon a reassessment of elevation data, coastal elevation data. And that was good because the previous assessment was based on SRTM, which was wonderful when I was a PhD student, but I think we have better now. And their reassessment of elevation data puts 250 million people in a situation of annual coastal flooding right now.
What was the controversial aspect about it? The methodology or the fact that so many more people are affected?
So there are a couple of controversial things. One was that the headline figure that's reported is the number of people that will be affected by sea level rise by 2100. And that ranges from 300 to 400 million people, depending on the emissions scenario and therefore the sea level rise. But what is seldom reported at the same time is that, for instance, if it were 300 million people, 250 million are already exposed. And so it's a small additional increase relative to that situation. So that was one of the controversial things in the way that it was reported. That's not the author's fault, that's newspapers, right? But the second controversial thing is that I think that the total, not many people recognize that 250 million people are exposed to annual coastal flooding right now around the planet. And it's probably because they tend to be not in the Western developed world, most of them.
I'm sorry, I'm going to try and whip through all these questions. So we have another question from Matteo. He's asking, can you comment a bit on how light absorbing impurities embedded within the snowpack/ice sheets impact the measurement accuracy via subsurface scattering?
Well, for radar and laser altimetry, the scattering horizon is one of our main challenges if we're looking for ultimate precision. if you're looking at Pine Island Glacier, it's thinning at 15 meters per year, and you don't need to worry about these things. And it's also essentially solid ice. But if you're looking at more subtle signals like Greenland in particular, where the firn pack is warming over time, then it does introduce significant problems. We have the perverse situation where a radar altimeter scatters predominantly from a high density surface. And what happens in Greenland is that the snow piles up in winter and then it compacts again to ice in summer. But the radar sees a very different signal. So the radar in principle penetrates the whole way through the snow layer and sees the previous year's summer surface until it melts, and then it jumps back up to the summer. So we see with a radar signal in places in Greenland, the opposite seasonal cycle to reality. And that does become a problem. A similar thing affects lasers as well. The laser altimeter doesn't know its scattering horizon. It just tries to make an estimate of it. And if you take a look at ICESat data, you'll get a point cloud of measurements from a location on the space. And in some places, it's a very stable, narrowly spread point cloud, and you can get a perfect estimate of the elevation. But in most places, there's also a distribution of heights. And the challenge is picking the actual height from that point cloud. It's very similar to radar altimetry, and that people have done some wonderful things with ICESat. You can see the surface and base of lakes, for instance, absolutely incredible work. And you can see through near coastal oceans to see the seafloor bathymetry. In atolls, for instance, you can see straight through crystal clear blue water, and the laser scatters from the seabed. So sometimes it can be really exciting to have this capability. But if you want to measure the elevation change of an ice sheet to millimeter precision, this is our main source of uncertainty, and that's where progress needs to be made.
Thank you. So we have another question from Olga. Perhaps maybe Olga asks, could you please expand a little bit on what Pine Island has been doing very recently?
Pine Island has not been, its rate of thinning hasn't accelerated recently. For those of you that have paid attention to it, its rate of grounding line retreat seemed to stop in about 2012. And that's because during the previous years, I don't think I have a slide of it, unfortunately, the glacier was retreating down a very steep slope on the bedrock. But it's now sitting, the grounding line, in a bedrock trough, where the ice above sea level steepens very, very quickly. And so we need to remove a lot of ice before the grounding line will retreat anywhere further backwards. That has stabilized the speed up as well for Pine Island. And Pine Island isn't accelerating significantly, apart from when icebergs break off. You'll have seen perhaps on Twitter and in the news, icebergs break off every now and then from Pine Island, and there's a force perturbation because of that. But there's nothing like the grounding line retreat feedback mechanism. For that, you need to move to Thwaites, where the rate of retreat continues and also continues to spread laterally as well. So Pine Island is confined narrowly within a trough, and so it can't spread laterally. But Thwaites is essentially getting wider as a glacier, which means the imbalance is still increasing.
So roughly how fast the peak is falling at the moment?
Pine Island, well, we have, you're going to catch me out because I haven't looked. It's about 4 kilometers a year. We've got a website with a near real time, our data portal has it on there with a near real time measurement of the speed for Pine Island and Thwaites, and it's probably on there. I'm going to guess it's 3.6 kilometers a year. I might be wrong. It could be 4, but it isn't changing significantly.
And the grounding line hasn't been moving since when?
We haven't tracked it. This is another capability we've lost. So it's one of those examples of an underappreciated satellite technology. Mapping the grounding line is most easily done with interferometric SAR data, but we have to have measurements that are shortly separated in time by about a week, and so we haven't been able to monitor it since about 2012. So it could have moved, but we can't be sure.
Okay, so effectively you don't know why it moved or not. That would be the answer. Is it correct?
So there, I mean, Olga, you know that there are other proxies for the grounding line, so you can look for the break in slope and things like that, and people don't see a break in slope, and so they believe that it hasn't moved, but we can't get the hinge line right now, and that's the problem.
I see. Okay, thank you. Thanks.
At this point, you should probably open things up.
I have a question. So you mentioned or teased briefly that IMBY has a new assessment coming out that says we aren't fated for the worst case scenario. Is this being driven by lower ECS in the climate models, or which I don't think that's what happens, or how much certainty can you say that we're not headed towards some of the worst case scenarios?
Oh, well, I mean, the extension for IMBY is just a few years. Okay, so the last update we had for Antarctica was ended in 2017, so 3 years ago, and for Greenland it ended in 2018. And so we've performed an update, and that update shows that the rate of ice loss from Antarctica has dropped, and so it's losing less ice now than it was in 2017. It was peaked then. And it also shows that Greenland went through, I think people know this anyway from anecdotal records, went through a very rapid melting period in 2017, and that's abated in the intervening period. It's picked up again now, but net together, the two ice sheets saw there's a significant peak in ice loss, in the rate of ice loss in 2017. So we've had 3 years of significantly lower ice loss, which brings us, if you look in the curves that we've plotted, CMIP5 versus IMBY, it brings us closer back down to the mid-range scenario.
So
and also there will be an update next month for those of you that are not involved in the CMIP6 projections for ice loss as well. And so it will be, I can't remember I'm a co-author, I'm apologizing now. I can't remember the details for the projections, but I think that they're more or less in line with SROC, which added an extra 10 centimeters to Greenland arbitrarily, but this is done properly.
Sorry, I was speaking out. Do we have any other questions from anyone? Give it a minute.
Pine Island was mentioned, what is Thwaites up to these days?
Yeah, Thwaites is still speeding up, but it's increasing its discharge more so because the glacier is widening. And so Thwaites, there was a lot of interest on Pine Island because it was the first of the two ice streams to activate significantly. But Thwaites is, by most people's yardsticks, the bigger concern for the future because there's less to obstruct its retreat. It's a very deep inland ocean basin, and so it can spread out laterally as well, the thinning, and so we do see that in the altimetry measurements. So I think Thwaites is still the bigger concern for the future.
Do we have any questions? I've got like a growing interest in icebergs. I wonder if I can ask you an iceberg related question.
Yeah, everyone likes a big iceberg.
Oh, yeah, I'm interested in small icebergs. So do you have an idea of what the smallest iceberg is that you can track and sort of like, is there some sense of a bias of because it'd be wonderful if we could have like a measure of the carving and where all that mass is going within the Southern Ocean, for example. But then I presume that beyond a certain size, you can't track. And how are they tracked? Are they tracked by eye? Do you use some kind of AI image recognition?
Well, icebergs, so we've become more interested in icebergs for various reasons, partly because we work now in partnership with the British Antarctic Survey, and they're interested in Brunt Ice Shelf in particular because of their base Halley, which is on it. And in about 2018, there were some big icebergs drifting around the Antarctic circumpolar current, which were worrying the Brunt Ice Shelf then. And they needed to know how thick these icebergs were in order to test whether they would come in and crash into the ice shelf and cause it to break away. And they didn't. So it averted a midwinter evacuation, which was important. So we started looking at them. And it turns out that lots of people are interested in them for different reasons, not just because they obstruct shipping routes, but because they disrupt marine environments, either when they're released or when they end up grounded somewhere else in the ocean. You can track them. We track them, first of all, using the National Ice Service, the US National Ice Service, which has a record for any iceberg of a certain size, and they chart its history, and it's manually done. And so people look through satellite imagery, hunt for the icebergs, and it's not automatic. We started to do some work to try and automate that, but it's not easy because icebergs rotate around, but also they break bits off them, and then they freeze up in winter, and so they become indistinct from the sea ice. But then worse still, in summer, if you're using radar imagery, the backscatter flips, and so while in winter they are darker than the surrounding, lighter than the surrounding ocean, in summer they become darker because they melt on their surface and they become very, very bright reflectors, and most of the radiation goes off in a different direction. So we track them in imagery, but actually you can see them in altimetry. And so there are some activities to spot them in an individual altimeter waveform. You can do that, but the problem with that is that you can't track them with that method because you can't be sure it's the same iceberg in a Lagrangian sense moving in space. For our work, the bigger the iceberg, the better. You saw a very big iceberg in the illustration I showed, A68. It's a huge iceberg. So it's actually 1 billion ton iceberg on its own. It's 300 kilometers long, and that works really nicely with an altimeter, just because you can recognize features. But in principle, with IceSat, there's no limit to the. IceSat has a footprint of 80 meters. So if it's small, if it's around 80 meters or bigger, then you can see it with IceSat too.
That's really neat. That's really surprising. Much smaller scale than I thought. But yeah, identifying them, as you suggest, sounds like a bit of a nightmare.
Well, this is what you pay machines to do, right? It's called machine learning. We don't see very much of it. People talk about it a lot, but they don't do a lot of it. And so it'd be really nice for somebody to take that on as a problem, because you'd have thought that a computer could probably track icebergs. They don't change in shape that much, right? And it's always in one direction. They don't grow. They always break up.
Yeah, I think there are a couple of people working on that exact problem, but I don't know off the top of my mind. And
icebergs
in
the southern hemisphere, icebergs are tabular because they break off the ice shelves, and so you get huge tabular icebergs. In the northern hemisphere, they're always tiny, and they're always they're just a point cloud. So the databases for icebergs in the southern hemisphere, they follow their trajectory, and so you can chart their position through time. But in the northern hemisphere, if you've got an oil rig in the Arctic, you just want to know the point cloud of icebergs that are surrounding your oil rig at the present time.
Do we have any other questions from the group? We should probably close off soon. Oh, there's a question from. Oh, there's a point from Helen, who is advertising a paper.
Hello,
Very
Helen.
good.
Hi, Andy. Thanks, Johnny, for letting me know about the seminar. I decided I'd come and listen. Thanks, Andy. That was great.
I apologize for being late. I hope it wasn't too inconvenient